Mass defect and binding energy. Introduction. Today, let's understand a very important concept, mass defect and binding energy. Here we have a pan. On the left pan, we have carbon 612 nucleus. Whereas on the right pan, we have 6 neutrons separately and 6 protons separately. And we found that the right pan goes down, showing that it is more heavier. Suppose we take a carbon 12 nucleus. It has 6 protons and 6 neutrons. If we add their separate masses, we get 12.09558 U. But the actual mass of carbon 12 nucleus is only 11.9967 U. Where did the mass missing go? That missing mass is called mass defect. Einstein said mass can change into energy. E equals mc square. So, this missing mass became energy when the nucleus formed. That energy is called binding energy, which holds the nucleus tightly together. Mass defect. Experimentally, the mass of the nucleus is less than the total mass of its individual protons and neutrons. This missing mass is called the mass defect del M. On the right pan, we have ZMP plus NMN. On the left pan, we have carbon 12 mass capital M. So del M equals ZMP plus NMN minus M. This is a very important equation. In the place of mass of the proton, we substitute mass of the hydrogen. And in the place of capital M, we substitute atomic mass. Here, Z, the number of protons, and N, number of neutrons, MP, mass of the proton, and Mn, mass of one neutron. Capital M is the mass of the nucleus. Some mass is converted into energy when the nucleus is formed. This is called mass defect, and the energy equivalent to is binding energy. Binding energy. According to Einstein's equation, E equals mc square. Binding energy equals del mc square. Binding energy is the energy required to break a nucleus into its separate nucleons. Binding energy is the energy required to break a nucleus into its separate nucleons. Be equals ZMP plus NMN minus M C square. Binding energy in terms of atomic mass. Since we usually know the atomic mass Ma, so the equation becomes binding energy Be equals ZMH plus NMN minus Ma multiply C square. Here MH is mass of one hydrogen atom. Energy equivalence to one atomic mass unit equals 931 million electron volt. The energy equivalent of one atomic mass unit 1 U equals del M C square. In the place of del M, let us substitute 1 U, 1.66 multiplied 10 power minus 27, and the place of C, let us substitute the velocity of light in vacuum 3 multiplied 10 power 8. On simplifying this, we get 14.94 multiplied 10 power minus 11 joule. Converting this into electron volt, we get 931 million electron volt. This is very important relation that makes our problem very simple. Energy equivalence to one atomic mass unit equals 931 million electron volt. Binding energy curve. Average binding energy per nucleon. The average binding energy per nucleon is the energy required on average to remove one nucleon from a nucleus. The average binding energy per nucleon is the energy required on average to remove one nucleon from a nucleus. So, the binding energy bar equals binding energy per nucleon B upon A equals ZMP ZMH plus NMN minus MA C square upon A. It shows how tightly the nucleons are bound inside a nucleus. This binding energy per nucleon value shows how tightly the nucleons are bound to nucleus. Here we have a graph. On x-axis, we have taken number of nucleons, that is the mass number. On y-axis, we have taken average binding energy per nucleon in million electron volt. We have done a lot of experiment and found the binding energy per nucleon for various nucleus and fixed the point on the graph. And we draw a line. This is called binding energy curve. When we plot average binding energy per nucleon, Be bar, against mass number A, we get a curve known as binding energy curve. When we plot average binding energy per nucleon against mass number, we get a curve known as binding energy curve. Important inference from the curve. 1. Rising region. Be bar increases with A up to A equals 56 ion. Maximum binding energy per nucleon is 8.8 million electron volt per nucleon. This is for iron nucleus that is become the most stable nucleus among all atoms. Second, middle region, the flat region where A is 40 to 120. Here, the binding energy per nucleon is approximately 8.5 million electron volt per nucleon. These nuclei are stable and non-radioactive. And the last region is a decreasing region. Here, the binding energy per nucleon decreases slowly after A greater than 120. For uranium, A equals 238. The binding energy per nucleon is 7.6 million electron volt per nucleon. Such nuclei are unstable and radioactive. So we have three regions. Beginning, there is a rise, and the maximum, and the third, the decreasing region. In the beginning, the atoms are stable. In the middle, the atoms are stable. But in the last decreasing region, the atoms are unstable and radioactive. Applications of curve. Nuclear fusion. Two light nuclei, atomic number, mass number less than 28, combine to form a nucleus in the medium size mass A approximately equals 56. Final nucleus has higher binding energy per nucleons, hence energy is released. Example, hydrogen bomb. Nuclear fission. Heavy nucleus, mass number greater than 200, splits into medium nuclei. A approximately equals 120. Final nuclei have higher binding energy per nucleon, so energy is released. Example, atom bomb or nuclear reactor.